Hello, welcome to the ninth lecture of the course Transportation Network Analysis. So, in the last class, we had just started to discuss about order of growth for algorithms. So, we will be continuing today on that. So, in this discussion, we will be focusing on asymptotic efficiency of algorithms. Okay. So, what does that mean? That we will be focusing on the running time of an algorithm as the size of the problem for the input that is given increases. Okay. So, this is saying the running time of an algorithm increases with the size of the input in the limit as the size of the increases without any bound. Okay. So, as I have been mentioning in the last lecture, we are interested in determining the computational time as the problem becomes very large, because that is when the challenge comes. Because when the input size is very large, the computational time can become very large also, and therefore in that situation we may not have that many choices of which algorithm to use and so on. So that is why we will be focusing on how well an algorithm performs as the parameter size n of the problem increases. So this is saying the same thing, that is the running time as the n becomes very large. So we are focusing on that situation of this problem here. So usually an algorithm that is asymptotically efficient will be best choice for all but very small inputs. So it is saying that an algorithm that is asymptotically efficient, that will usually be a very good choice, just that for very small inputs you might see that algorithm may not be the most efficient algorithm to solve, and you might have choice of selecting slightly better or more efficient algorithms. For example, I had taken last time, we had first algorithm taking C1 n square operations and the other one taking C2 n log n. So when this is the computational time that we had chosen for the first algorithm, and this is the computational time we had chosen for the second algorithm. So when C1 is suppose 2 and C2 is equal to 50. So when n is, for example, very small, okay. So in that case you will see that the first algorithm is more efficient as compared to the second algorithm, okay. But eventually as the size of the problem will increase, this will become larger as compared to C2 n log n, okay. So that is why since our priority is to choose an algorithm that will be more efficient when the size of the problem is very large, so that is why we will be going with this algorithm C2 n log n, even though this may not be the most efficient algorithm when the size of the problem is very small, okay. So now we will be defining this capital O notation that is used for asymptotic upper bound here, or equivalently it is also called the worst case running time. So for a given function gn, we denote by OGN the set of functions given as follows. So OGN consists of all those functions fn such that there exist positive constants c dash and n naught, such that fn is greater than equal to 0 and fn is less than or equal to c dash gn for all n greater than equal to n naught. So let us take a deeper look at this definition here. So let us maybe see this through a diagram here. So in the x axis we are plotting n here, and suppose this is that function fn here, okay, and suppose this is the function c dash times gn, okay, and suppose this point where c dash n is overtaking fn be n naught. So this definition is saying that we can say that this function fn is belonging to this set of functions OGN, or we also say it in this way, that fn is of the order gn if there will be some point n naught beyond which this function fn will be upper bounded by c dash gn. So this is what it is saying. So After this point n naught, we will see that from here onwards, this c dash gn will never be below fn. Okay. So, in that way we have said that there is an upper bound on the value that this function fn will take after n is greater than or equal to n naught here. So, this is what it means here. This is a very important definition. In order to understand this further, we will be taking a look at various examples. So, we write fn is equal to OGN to indicate that a function fn is a member of the set OGN. Okay. So, ideally, I mean, we should have maybe written that fn is an element of OGN, but in this literature it is also written that fn is equal to OGN. So, it means the same thing, that it satisfies this definition we had seen in the last slide, that this function fn will be less than or equal to some constant times gn for all n greater than or equal to some constant n naught. Okay. Okay. Now, let us try to understand this through an example here. So, let this function be fn. Okay. So, fn is equal to half n square plus 3n, and let gn be n square. Okay. So, we need to prove that there exist c dash and n naught such that this half n square plus 3n is less than or equal to constant c dash times n square for all n greater than or equal to n naught. Okay. So, we just need to come up with one set of values of c dash and n naught such that this condition is satisfied, and if we are able to do that, then we can say that this is correct, that this function half n square plus 3n is of the order n square, or it belongs to the set of functions O n square. So, now you can see that why we had previously mentioned to throw away lower order terms for a n square plus b n plus c, where n is sufficiently large. Okay. Because we will be able to see that even if instead of this 3n, if it was say some other term, but still not a term that is growing faster than n square, but like for example, if instead of 3n we had suppose 6n or 2n, it does not matter. Even then we would have said that this function fn will be of the order n square. Similarly, this constant half is not important here. Instead of this half, if it would have been even 100 n square plus 3n, then also this function will be of the order n square. Okay. So, that is why we had said that this constant a and these other two terms bn and c, they are not important when we are classifying whether this function fn is of the order some function gn or not. Okay. So, we will now justify that intuition using the formal definition of this capital O notation. Okay. Let c dash be equal to 2 and n naught be equal to 2. So, we are saying that the set of pair of values c dash and n naught for which this condition is satisfied, this is one set here. Okay. So, we can check this. So, let us do that here. So, let us see whether this holds or not. So, we want to prove that half n square plus 3n is less than or equal to 2n square for all n greater than or equal to 2. So, this symbol is for all. Okay. So, let us take this term half n square on the right hand side. So, we will get 2n square minus n square by 2, and therefore, we get 3n is less than or equal to 3n square by 2, and therefore, we get n is greater than or equal to 2, and this is what we had claimed here. So, for n greater than or equal to 2, this holds, and therefore, we have now verified that this function fn, which is half n square plus 3n, that is less than or equal to c dash times n square for all n greater than or equal to n naught, where the c dash that you can choose is 2 and the n naught you can choose is also equal to 2. Okay. So, we just proved this, so that half n square plus 3n is less than or equal to 2n square, and this holds for all n greater than or equal to 2. Now, one thing to note here is that these values c dash and n naught, they need not be unique. For example, you can choose c dash to be equal to say 4 and n naught to be equal to 2. Even then you will be able to prove that half n square plus 3n is less than or equal to 4n for all n greater than or equal to 2. Okay. Similarly, you can suppose choose c dash to be equal to 2 and you can choose n naught to be equal to 5. So, even then this will be satisfied that half n square plus 3n is less than or equal to 2n for all n greater than or equal to 5. Okay. And this one is very simpler to see here, that if this condition is holding for all n greater than or equal to 2, it will also hold if n is larger than 2 here. Okay. So, we just need to come up with one set of values of c dash and n naught if we have to prove that a function fn is of the order gn. Okay. Now, note that if a function fn is not OGN, that is, it is not of the order gn, then you will not be able to find any pair of values c dash and n naught that will satisfy that definition. Okay. Okay. So, let us now consider another example here. Now, we are saying that n plus 1 is of the order n square. So, this is interesting here. So, note that n plus 1 is of the order n square, it is also of the order n cube. Okay. Because in the definition of capital O, we have this inequality. Okay. So, that is why this is correct. So, again, in order to argue this, we need to come up with the one set of values of c dash and n naught that will satisfy this condition, that n plus 1 is less than or equal to c dash times n square for all n greater than or equal to n naught. Okay. So, we are given that one set of values is c dash equal to 2 and n naught equal to 1. So, let us check it here. So, n plus 1 is less than or equal to 2n square, okay, for all n greater than or equal to 1. So, this is true. Okay. So, therefore, these set of values c dash equal to 2 and n naught equal to 1 is correct. Okay. Let me maybe give you an example where a function fn will not be of the order gn. For example, this function n square will not be of the order O n, okay, because you will not be able to find any such pair of values c dash and n naught for which n square is less than or equal to c dash times n for all n greater than or equal to n naught. This is just not possible. Okay. Why is this not possible? Because this function n square grows faster as compared to this function n. Okay. So, if this has to satisfy, so then it means that after this value n naught, this n square will get upper bounded by this function constant times n here, and that is just not possible, because this function n square, if we are plotting n on this x axis here, this grows something like this, okay, and whereas this function n will pass through the origin and it will grow like this, and if it is c dash times n, so then it will be growing something like this, okay. Sorry, so it will be actually be growing like this here, not this like. So, it will be going at a faster rate, but it will still be passing through the origin here. Okay, so you can see that this will never be the case. So, after some point n square will overtake this function c dash n here. Okay. So, this is saying the same thing, that n plus 1 is less than or equal to 2n square for all n greater than or equal to 1. So, this holds. Okay. So, now we have defined a way to characterize that whether a function fn can be said to be of the order OGN or not. Okay. So, now let us look at polynomial time algorithms. What do we mean by polynomial time algorithms here? So, we say that a function fn is polynomially bounded if fn is equal to capital O nk for some constant k. Okay. So, k can take any value here. If k is equal to 2, then also it is fine. If k is equal to 100, then also it is fine. So, one way to say that an algorithm is efficient if the running time of that algorithm is polynomially bounded. Okay. So, now this is very interesting here. We are saying that if the running time of an algorithm is taking polynomial operations, then it is an efficient algorithm. So, such algorithms that are polynomially bounded are called polynomial time algorithms. And there are several reasons that make polynomial time algorithms desirable. Okay. So, just to give you an idea, here we are now clubbed all the algorithms that take polynomial time into one category here. So, now whether an algorithm takes of the order n square operations or it takes of the order n cube, this difference is not that important at this point as compared to, for example, if an algorithm is taking exponential operations. Okay, if it is taking, say, the computational time or the running time of that algorithm is suppose of the form 2 to the power n, where n is the size of the input here. So, then this function 2 to the power n, you cannot express it as some O n k, where k is a constant here. That is, this exponential function cannot be upper bounded by any polynomial function. Okay. So, then it means that this function 2 to the power n is growing at a much faster rate as compared to all the other polynomial time functions, and therefore, this 2 to the power n comes in a different category altogether. So, this difference n square versus n cube is not that big of an issue now, just that if an algorithm can be expressed by having its running time in the form of O and k, then it is great. Okay. So, one of the reasons why polynomial time algorithms are important is that this property that polynomials are closed under addition, multiplication and composition. What does it mean? That first thing, they are closed under addition means that if you add two polynomials, you will get another polynomial. For example, if you have a polynomial n square plus 1 and you have another polynomial n cube plus 2n plus 1, and when you add both of them, you will still be getting a polynomial function. Okay. Similarly, if you do multiplication of two algorithms, it will still be a polynomial. For example, now suppose you multiply n square plus 1 by this n cube plus 2n plus 1, this will give you another polynomial. So, the addition of two polynomials gives a polynomial, multiplication of two polynomials gives a polynomial. Similarly, this is also very important, composition also results into polynomial functions. That is, if the output of one polynomial time algorithm is fed into the input of another, the composite algorithm is polynomial time. Okay. So, for example, in this function n cube plus 2n plus 1, suppose instead of n you have n square plus 1. So, n square plus 1, we are doing cube of that plus 2 times of this n square plus 1 and then plus 1. Okay. So, instead of this function n cube plus 2n plus 1, here I have replaced n by n square plus 1. So, what we are doing here is that we are taking the output of one polynomial time algorithm, which is this n square plus 1, and we are inputting it into another polynomial time algorithm that takes n cube plus 2n plus 1 operations here. So, this will also be another polynomial, okay, whose power, the term with the highest power will be still n to the power 6 here, and then we will be having other terms here. Okay. So, this property is very important Why? Because for example, if you have a very complex algorithm and that has many parts, okay, so then in order to determine how much running time that algorithm takes, we can determine what running time these individual parts of that algorithm take. And if for example we find out that one part of this algorithm is taking n square plus 1 operations, the other part is suppose taking n cube plus 2n plus 1 operations. So when we add together these two parts to make that original algorithm, then it will still be a polynomial time algorithm, because the addition of these two polynomials is also polynomial. Similarly, there are these complex algorithms where we have multiple loops and so on, okay. So we might be implementing smaller algorithms which might be providing outputs to larger algorithms. So there this composition property is useful. So there, since we will be using the output of one polynomial time algorithm and we will be feeding it into the input of another, we will be still be able to argue that the running time of this overall algorithm will still be having polynomial time. That is why in the analysis of these algorithms, this property that polynomials are closed under addition, multiplication, composition, that helps a lot. Okay. Now, another very important aspect that says that why polynomial time algorithms are important is that experience has shown that once the first polynomial time algorithm for a problem is discovered, more efficient algorithms follow. Okay. Now, to give you an example, let us go back slightly into the history. So, for linear programming, or LP in short, there was this algorithm called simplex algorithm that was discovered long time back, around 1950s or something like that, and that was very efficient for almost all the examples of linear programs that we had. It used that property that the optimal solution of a linear program lies at one of the extreme points or the corner points. But some researchers later found that there are some special cases of linear programs for which this simplex algorithm can take exponential amount of time as the size of the problem. So in that way, this simplex algorithm was not a polynomial time algorithm, because it did not take polynomial number of operations for all the inputs or all the examples that are possible for the linear program, okay. And then therefore the search went to determine polynomial time algorithms. So one of the first polynomial time algorithms that got discovered for linear programming was this ellipsoid method, which was discovered in 1970s, and that was a major breakthrough, just that it was not very efficient in practice, and therefore the search for more efficient polynomial time algorithms went for linear programming. And then finally in 1980s, Narendra Karmarkar discovered these interior point algorithms, which are polynomial time algorithms, but they are practically very efficient, and nowadays if you will find any solver which is solving a linear program, it will be having one of the variants of this interior point algorithms, okay. So that is why one of the major issue was that until the first polynomial time algorithm was discovered for linear program, it was not clear whether we will be able to find a polynomial time algorithm for that linear program or not. And once the first polynomial time algorithm is found, then the situation becomes slightly better, and over time more efficient algorithms get discovered, and that happens for other problems as well. And the other reason is that these polynomial time algorithms scale much better than other algorithms. So for example, if there is an algorithm that is not polynomial time, okay, so for example, if an algorithm takes 2 to the power n operations, okay, so this function 2 to the power n grows very fast, faster than any of the polynomials. For example, it grows faster than say 2 to the power 4 n 100. So I put very large constant values and the exponent values for this n, but even though this is a polynomial function which seems to be growing very fast, there will be a point at which this 2 to the power n will become larger than this function, okay. So we will be seeing some more examples to understand and appreciate this fact in the next class. Thank you.